Hi, I'm going to go through this example of finding the terminal velocity of a falling loop. Before I start, I'm just going to strongly suggest that you go back to your first semester notes and review the way that we solved the terminal velocity problem for objects that are falling through fluids, such as air. Because the math that I'm going to refer to in this video is going to really relate back to that example. And if you're not familiar with that, you want to take some time to look at that first, okay? Because I'm going to solve this problem, but I'm going to solve it by an analogy to the terminal velocity that we solved back last semester. All right, so I'm going to read the situation here. The situation says that you have a very long rectangular loop of height L, mass M, and resistance R that starts from rest and falls downward into the uniform magnetic field that is shown. Assume that the loop is very long, such that it never completely enters the magnetic field that it's being pulled into. Okay, so we can look at the picture. You can see you have a very tall loop, right? The L dimension of the loop is kind of like how long is it sideways, right? So L is the sideways length. But the vertical length, right, the up and down length is like super long. So we'll just say, put the little marks there, right? So it's very long. Also, this loop has kind of a resistance to it. So I'm going to put a little resistor symbol here. And that might just be due to the resistivity of the loop material itself. Okay, so what's going to happen here is that the first question asks about, is there going to be a current that is induced? And then after that, it's going to ask questions about, well, what are the consequences of that? And a consequence is going to be that, yes, a current is what will be induced, but also that current is going to cause an upwards force to act on this loop. The magnetic field is going to push up on it and slow it down. So let's answer this first question. So when the loop first enters the field, in what direction will the current be induced? So let's just look at the bottom part of the loop, this part that's down here, right? And as you think about it, right, the loop, here it is. It's got some kind of area vector, which I'm going to make pointing out at us. And then I'm going to, as you can see, it's falling into a magnetic field, which is pointing in. So there's an external field, which is pointing in. And we know that when this happens, that when more and more of the loop falls into this field, that you're going to get more and more negative flux. Why is it negative? Because the area vector and the B vector are in opposite directions. So the response to this is going to be that the loop will try to do this. It will try to make a magnetic field which is pointing out of the page, right? Because it's trying to oppose the change in flux. It's trying to keep the flux from becoming negative. So it will induce a current to make the magnetic field come out, okay? And in order for that to happen, that means that there must be an induced current which goes in the counterclockwise direction. So something like that. And so that's just thinking about it from a Lenz's law point of view or a Faraday's law point of view. All right. So the loop tries to maintain the status quo. The loop tries to resist the increase in negative flux. And it does that by making that red field. Okay. For the next question, which way will current flow? I think we've already answered that. And then will there be a magnetic force on this current? If so, which way will it act? Well, here's where it gets interesting, right? So let's draw the bottom of the loop. And we have just established the fact that, yes, there will be a current. The current will go that way. And then you have a current, so it's traveling from left to right. But there's also a magnetic field, right? You also have this. And so you're going to use the right-hand rule now. And what's going to happen is, I'll just draw this over here, is you try this, but if you put your fingers in the direction of the current and your palm faces into the page, you're going to get an upwards force here. That's a magnetic force. So I'll call it FB because it's the force of the magnetic field pushing up on the rod. That is the force that is like a braking force that slows it down, okay, or that pushes up on it at least. And so that's the force that's going to cause the loop to reach a terminal velocity, okay, eventually. So I didn't draw the gravity force on it yet, but we'll do that later on. But for now, maybe I should do that. So let's just draw, there's a gravitational force also, right? There's like an Fg. And the magnetic force is going to take some time, right? It's going to catch up to that gravitational force. And eventually they're going to cancel each other out. And that's when you reach terminal velocity. All right, question C just says, will there be forces on the sides of the loop, the vertical edges? The answer is yes, but the forces cancel. Again, if you can probably just use a quick sketch here to show that. But if current is going up here, it must be going down here, right? And by the right-hand rule, if your magnetic field is going into the page, then you'll have an inwards force on the right side of the wire and an inwards force on the left side of the wire. Keep these straight. There. And so, yes, there are forces that act on the sides, but the sum of the forces in the x direction is equal to 0. So they cancel. So they don't really do anything. So really the only thing that's happening here, the only interesting part is this bottom part of the wire, right? That's the part that's experiencing that force. All right, so now let's write Newton's second law. So we know that F net equals ma. And in this case, okay, so for F net, let's see, let me draw my picture here again. So copying that down, I've got F gravity, I've got FB, right? Those are the two forces that act on it. I'm going to say we'll make Fg positive. That means that Fb is in the opposite direction. It's negative. That's equal to ma. Okay. And then what you can do is you can go ahead and plug in, right? So gravity is mass times g, gravitational acceleration. And hey, what is the size of that magnetic force that's lifting up? The size of that goes back to ILB. Remember that? So that's something you should know from before. So the magnetic force is ILB, current times length times magnetic field, and is equal to m. And this is where your dv dt comes in. So you've got a differential equation. And the other thing you keep in mind here is you've got this now. So this should look kind of familiar, right? Differential equation. But you do have a current that's going to be changing, right? Because the loop is going to be changing its speed. So we're going to do a little substitution with that. We go back to good old Ohm's law, right? And so if you have this piece of this length of wire which is falling in a magnetic field, the EMF is going to be equal to BLV over R. So again, you should remember that. If you don't, why don't you pause and look at your notes? But the EMF that acts across the wire, the length of the wire, is going to be equal to BLV. Okay, so you substitute in. We have so many things happening here, but let's just continue on. Be strong. So I'm substituting in for I. Okay. And then, so that makes it a little more complicated, but I'm going to then finally write as simple as I can get here. I'm going to put the dv dt in front. That means I have to divide out. Actually, let me leave the m in front. Okay, we'll keep that there. So I'll have m dv dt plus, right, plus b squared L squared over R times V minus mg equals 0, right? So you just check my pluses and minuses on there, but I had to move things around. So this formula, this is the differential equation that we wanted to get, and we've put it into the form that's kind of a standard form, okay? So the derivative's out front, and then the v, right, the v, I'm going to go over that in red. The v is the function that we're going to be solving for, and you can see it pops up in two places, okay? And so we're going to show that velocity initially gets faster, but then eventually it stops gaining speed, kind of flattens out. It reaches a terminal speed. Okay, the next part here is saying, it says use a differential equation that you wrote in its limiting form to find an expression for the loop's terminal velocity. Note that you do not need to find a full solution for the entire equation. Yay. So what this means is that when you're at terminal velocity, when you, after like, let's just say after a lot of time has gone by, that you will no longer be speeding up. You will no longer be accelerating, right? Your acceleration is going to be equal to 0. You're moving, but you're just not going faster. You're not gaining speed. And so you can see, if you take that and you plug that up into the top equation, that it knocks out this first term, right? And so that simplifies the equation. So let's see what happens. So we're going to end up with b squared L squared over r. And then we're going to multiply times the terminal velocity, right? This is a very specific velocity. It's not the function anymore. It's just a number. Is equal to mg. See what I did? So that's taking this part of the equation here. But again, the v here is no longer a function. That's actually just like a limiting value. And then you can actually just rearrange algebraically to come up with an expression for that value. Things that you, so this is the result here, right? So if you want to know how fast the loop will eventually fall, this is how fast. It's kind of crazy, a lot of things in there, right? But you should think about the physicality of the different things, right? So if the loop weighs a lot, it's going to have a very fast final speed. If the magnetic field is very weak, right, it'll have a fast terminal speed. If the loop is very narrow, it'll have a fast terminal speed. And then the weird one is the resistance. If the loop has a low resistance, a high resistance. If R is big, it'll also reach a fast terminal velocity. And think about why that might be. If you have a high resistance, right, that means that the loop is not inducing a lot of current. And so there isn't going to be a lot of pushback. Sorry about that. That was a random Windows photobomb of my screen. Okay. So anyway, think about what those factors actually mean and why they mean it. Okay. All right. Now let's continue on. We're going to kind of keep it moving here. This again is where you really want to remember stuff from before. We solved the differential equation before for terminal velocity. K here was called the drag coefficient, right? Drag coefficient. And you can look at your notes on that, but this is your differential equation that we had for something falling through the air. And it looks kind of like what we had before from up here, right? The formula that I put a box on. So if you look at the K in this formula right here, look at the stuff that would show up in the K position in our differential equation upstairs, right? So what we're going to do is we're just going to postulate that for a falling loop, the K is equal to that stuff that comes in front of the V. So it's going to be equal to B squared L squared over R. And so this is kind of like a drag coefficient for magnetism in this situation. Okay. That's useful because we can actually still make the analogy to all the math we did earlier for terminal velocity, and we can take shortcuts. So one of the things we discovered earlier last semester was that for something falling through the air, the time constant goes as the mass of the object divided by the drag coefficient. Well, that same math is going to be useful to us for the loop, except we just kick out the K and replace it with this. And so we'll have a way to find the time constant. So I hope you can see when I do that and I substitute that stuff up here in for K, I'm going to end up with mass times resistance divided by B squared L squared. And I'm going to ask you again to just think about the physics part of that, right? If you have something which is doing an exponential decay with time, it can either take a long time with a big time constant, or it can get the job done quickly with a short time constant. And so it's worth having you think a little bit about, if you have a loop that's falling, what are the factors that make the time constant either small or large, right? And I'm going to let you think about what each of those factors mean. And hint, hint, it's very similar to the things we talked about earlier there, okay? So again, what we did here is we came up with a time constant without actually solving the whole differential equation. We just made an analogy. Okay, let's do a quick verification here. Let me switch back to blue. And the idea would be verify that the weight of the object is equal to k times the terminal velocity for magnetic drag. Okay, so let's see. What is k times terminal velocity? K times v terminal velocity. We have things we can substitute here, right? K from upstairs, weight from up here is equal to b squared L squared over r. And then terminal velocity, I got to go back and look at that. That's over here. Let's get that stuff out of there. So terminal velocity is this. So that's mgr divided by b squared L squared. So I'm plugging in my magnetic specific equations here. And I hope that you see that lots of stuff goes away and leaves you with the weight of the loop. So again, this should make sense to you if you remember stuff that we did in the fall with terminal velocity. So you got to remember that we said that the weight of the object is related to the terminal velocity multiplied by the drag coefficient. Okay. And the last thing that you really should remember is that if you have something which is falling through the air, the terminal velocity follows a formula like this. Okay, which it does. So this formula works for both air and for magnetism. Okay, I'm going to jump down to this last part. And so in other words, if you graph that function, right, that's totally the graph that does this. Something versus time, right? Maybe velocity versus time. And then you'll have some kind of an asymptote, or you have an asymptote here, right where you've got your terminal velocity, whatever that number is. Okay. So this expression up here is really important. That shows up in a lot of stuff we've done this year. Now for air, you had things like the terminal velocity. Oh boy, what was that? Is equal to mg over k. Okay. And for air, you had tau is equal to m over k. Those are things that you should recall from before. We probably mentioned a few of those here. But for the loop, for a magnetism with a loop, we have slightly different things happening, right? It's a little more complicated. That limiting value for the terminal velocity is now, looking upstairs, it's mgr over b squared L squared. And the tau, the time constant, is also kind of complicated. It's mr over b squared L squared. So, the thing would be like, you just have to recognize that. And so if you know the values of the mass and the resistance and the magnetic field and the length, you can actually plot graph with numbers, right? And so you would need to know those specific values for the loop problem in order to actually graph something with numbers. But the point is that both the loop and something falling through the air eventually reach some kind of a top speed. That's the point of this whole example. Okay, they both reach a top speed, and it takes a differential equation to actually kind of solve for this function here that I put the star by. Again, please review your notes for terminal velocity and air, and that also will help you a lot to strengthen your skills that you need for the AP test. Hope that was helpful.